times x2 plus the third row times x3, which equal to 0. And this leads to that A of x is a linear combination from the column space of A. Okay, we will have an illustrative example just after this slide. Also, we can conclude that Ax is always a vector in the vector space of A. Also, we can conclude that rank of A equal the dimension of column of A equal the dimension of row of A if we have M of n, and the rank of A equal to the rank of A transpose. Let's see this example. This example is a very, very nice one. It will show you how Ax is a linear combination from the vector space of A. Let's get back again and remember. How to prove that a vector is a vector's combination or from another vector, from a vector space. Simply, if I succeeded in getting C1 V1 plus C2 V2 plus C3 V3 equal to U. And this is very simple. See? Remark that Ax is always a vector in the vector space of A, as it is a linear combination from A. How to prove this? It's very, very simple. This is the linear combination formula that I'm telling you about. Any vector belongs to a vector space can be explained as coordinates times the set of vectors generating to this vector space. So now I have the coordinate which is C1 up to Cn for this transform. If you remark A times x, it is simply multiplying the matrix A by x1, x2, x3, which is exactly like the coordinates. So multiplying or solving the system Ax, it's exactly like multiplying the first row by x1. See, once you multiply the first row by the column, this is the first row, this is the second, this is the third. Which means I can separate a column for x1, a column for x2, and a column for x3. This is x1, 0 and 0. This is x2, 2x2, and x2. And then finally x3, 4x3, and 2x3, as you can see. I can take x1 as a common, x2 as a common, and x3 as a common. Look to this 4. It's a coordinate. It's exactly like this one. C1 times V1, plus C2 times V2, and so on. This is C1, which is x1, times the first row in the matrix, or I'm sorry, the first column in the matrix, plus x2 times 1, 2, 1, which is the second column in the, or the second vector in your vector space. And the last one is the third vector in your vector space. So I can write, really, Ax is a linear combination in the space of A. This completed as, which is a linear combination of the vectors. Here, if you have a problem, instead of having, I like this problem better than the coming one, which explains actually how A and X are a linear, how A is a linear, or the Ax is a linear combination or a set from the vector space of A. Here also can be written in specific number. He's telling you that you have A, which is double. These are the vectors of this vector space of A, 1, 0, 0, 1, 2, 1, 1, 4, 2, and you have X, which is 1, 2, 3. If I want to write a linear combination, or to show that, it's really very simple. All I have to do is just directly, just within a second, once more, let's read our problem, which states that consider A, which is, consider A and X, write Ax as a linear combination of the columns of A. So I won't write Ax as a linear combination of the columns of A. So all I have to do is to take the first column, which is simply 1, 0, and 0, and I will multiply it by the first number, which is the coordinate of the first vector, plus 2 times the second column, which is 1, 2, and 1, and then plus the third coordinate, which is 3 times the third column, which is 1, 1, 4, and the 2, and the result will be A times X as values, as you will see shortly. So, if I want to do this, okay, use once more, strong. Okay, here is the A matrix times 1, 2, 3, which can be easily put as 1, 2, 3 times the columns of matrix A. If you try to multiply them, which explains that AX can be written as a linear combination from the vector space of A. So all I had to take is the first, the vector or the column of each vector from this matrix, and then multiply it by 1, 2, 3, which are the coordinates of X. He's stating that let A, M, and N be a matrix, okay? The solution set of any system of equations, I've tried to explain that by the beginning of this lecture, that if you are trying to solve a system of equation, AX equal B, you have three cases if you remember. You have a unique solution, which happens when augmented matrix rank equal to the A rank and the equal to the number of unknowns. And then you will have a set of solutions, which are numbers, just one set of numbers, which could be the value of XP. This is actually for the case of unique solution. If you have infinite number of solutions, then the appearance of null of A will appear to you. You usually will have some numbers plus some relation between the variables. And this is what we had in the last problems by getting the solution of AX system. So what I mean is the solution set of any system of equation equal to a particular part related if you have a B part plus the homogeneous part for the solution of this system. If I solve AX equal to 0, this is what we got by null of A. This is what we did previously. So this is mainly the solution set. This is the general form of a solution for a system of equations in all cases. Okay. Remark that we can say that the solution set is a particular part plus the homogeneous part. The homogeneous part, which stands for AX equal to 0. The particular part will happen only once you have the B value for the non-homogeneous set. In order to explain this more, let's solve this system, which consists of 0, 3, minus 3, 1, 0, 1, and it's solved for B equal to 6 and 1. As you can see, Mr. Firas, if this is going to develop a unique solution, if this system can develop a unique solution, no way.
I don't know.
ليه no way? ليه no way? لأن ال A matrix, how many equations, Mr. Firas? 2 equations. You have 2 rows,
Yeah.
so it's 2 equations. صح? In how many columns?
3.
Which are 3 unknowns.
Okay.
So you have 2 equations and 3 unknowns. So the only thing is to have infinite number of solutions.
Okay. They have
How
to
to
be rows and columns have to be the same for it to be.
If you have a unique solution. So let's try to solve this system. Okay. Now I will need to go through AX equal B. On an augmented matrix form, it's gonna be 0, 1, then I will have 3, 0, then negative 3 and 1, and the B column, which is 6 and 9. I will try to go for the reduced echelon form in order to get our solution. Let's go through it. The first step, it's gonna be getting a pivot for the first row. How to get a pivot for the first row? How to switch these 2 equations. So it's gonna be 1, 0, 1, and the result is 9. And this is gonna be 0. I will divide on 3, so it's gonna be 1, negative 1, and 2. I believe now on this form, we have reached the reduced echelon form. So, first of all, we've just replaced these 2 rows
Divided by
the each of each other, and then we divided the first row by 2, so it comes to this one.
by 3.
Okay, try to write me the solution set, please. So the solution set states that I have x1 plus x3, which is supposed to equal to 9. For the second row, it's gonna be x2 minus x3, which is supposed to equal to 2. And from this set of variables, I can state that x1 equal to 9 minus x3. And x2 will equal to 2 plus x3, which can be rewritten as the solution set that we need to see contains x1, yes, x2, and x3. That's the result, the solution set, which can be written as a first numbers, which is the particular solution, 9, 2, and 0, because we don't have x3. And plus negative x3, then x3, then I will have x3 here. And this is for the last value. Take x3 as a common, so I will have 9, 2, and 0. And finally,
Why is the first x3
plus
negative?
take x3 as a common, which is gonna be negative 1, 1, and 1. Am I right?
Why is the
Okay,
first
what's your question?
Why is the first x3 negative?
9. Because once you try to expand this equation, so it's going to be 1 times x1, 0 times x2, 1 times x3 equal 9.
Okay.
And for the second one, it's going to be x2 minus
Ah,
x3 equal 2.
I got it.
And then I will try to move these values to the other side. Then I rewrote them. The numbers which is related to the existence of the b values. صح؟ لذلك بقوا هنا 9 و 2 و x3 doesn't exist, so it's 0. Okay, for this part, which is negative x3, positive x3, and you will have another x3, so you will have negative x3, x3, and x3. Take x3 as a common, so this is the set. If you remark, that's the solution set consists of xp, which are the particular solution, plus the null, and of course here x3 belongs to R, the null of A, which is negative 1 and 1. So, what we saw is an evidence that the general solution for a system of equation can be written exactly as an xp plus a null of A. xb, which is related to the existence of the column value, of the b value, plus the null set as you see. In a similar manner, here we go, let's solve the system. On the reduced echelon form, these are the values relative to n and 2. This will imply x1 plus x3 equal 9, x2 minus x3 equal to 2, which can be rewritten on this form. And simply, I can separate the values as we saw right now. So it's gonna be 9, 2, and 0. And then you will have negative x3, positive x3, which is going to imply negative 1, 1, and 1, exactly like what we saw in here. So this is a stand relative to the existence of the 6 and 9. And this is what we called the null of A. So now we know that if we have inhomogeneous system of equations, we will get the null from the homogeneous and the particular, depending if you have B or not. This, شفت القلم صح. Okay, so and K of course belongs to 1. Okay, that's the span, so it's 9 to 0 plus the span of negative 1, 1, and 1. This is just only the numbers, 9 to 0s, and this will depend on the value. All the vectors will be on this form. So simply multiplying the scalar and you will have a solution for the system. Okay. we can write a classification for a system of equations like this. Okay, if you have B belongs to the column space of AX, you will have consistent system. If you have B doesn't belong to the column space of A, then you will have no solution. So if the B was a linear combination from the AX, you will have a consistent system. If not, you won't. Okay, remark, that's the solution set. Okay, if I have B belongs to column of A, if the null A doesn't exist, if this part doesn't exist, you will have a unique solution. If this one exists, it means you will have infinite number of solutions. That's exactly what's stated here. For the consistent independent set, it will happen when the null equal to 0. You don't have any of the variables depend on the others. You have results for the variables. This will happen only if you succeeded in getting this on the reduced echelon form of a unit matrix, and you will have x1 equal to value x2 and x3 exactly the same. It's written also here, B belongs to the column space of A. Here, that will make it consistent. If not, it's not. Okay, the null A is the homogeneous solution of AX, because when you are studying, sometimes you will lose your way. What's null A? Null A is the solution of a system if it was homogeneous. Okay. Okay. So once more, this is if null of A equal to 0, you will have the independent solution. Otherwise, you will have the consistent system, and dimension null of A will be more than 0, because you may have one variable depend on the others, and so on. From all the previous, rank of A equal to n, A is invertible if the rank are the same. All of this, they have the same meaning. Okay. A can reach unit matrix, which means you will have a unique solution. AX equal B is a consistent independent system. For every B belongs to Rn. Column of A equal row of A equal Rn, because you have a consistent independent system of equations. Null of A must equal to 0. This part will disappear if you have a unique solution. The rows of A vector of Rn form a basis of Rn, and the column of A also a basis of Rn, because simply you will have n equations in n amounts, which makes sense. The last thing is we can look to A times X as a linear transformation, because we already know that linear transformations are simply A, which is the reducer matrix, times X, which is the volume, which is the vector that you are going to transform. And this is mainly how you move from R2 to R3. The kernel, this is just to remember the linear transformation. If we are moving from Rn to Rm, it's called the linear transformation. The transformation matrix is the A matrix times X. We have plenty of exercises on this. Okay? The result will be called the kernel of T. So kernel T is simply the null of the A matrix. يبقى لما اطلب منك انك توجد الكيرنل، ده معناه انك تصولف السيستم AX ايكوال كام؟ 0. يعني تحل السيستم وتجيب النمبر. طيب ايه هو الرينج؟ لان انا عندي الدايمنشن بتاع الرو بيساوي الدايمنشن الكولوم بيساوي الرانك بتاع الاي. كمان عندي ان الدايمنشن بتاع رو اوف اي بيساوي الدايمنشن بتاع النل اوف اي as seen previously. يبقى الرينج اوف تي بيساوي الكولومز اوف الفانكشن اوف الكولوم سبيس بتاع الاي. اوكي؟ برضه مكتوب لك هنا dimension بتاع null A of T plus the dimension of columns of A of T equal n. I will send you these slides inshallah today. Okay? Which, as you can see. So, the dimension of the curve plus the dimension of the range, which will equal 2n, and this is also a statement in the linear transformation. You'll find it connected together. And this will grab our eyes to this fact. T, the transformation, is injective if and only if the dimension of the kernel equal to 0, which means you don't have null. So you will have injective function, just only a unique solution. The value of x1, x2, x3 equal these values only. You don't have a generating function. And it will be surjective, okay, just a second. So this is the unique solution, as I told you. And it will be surjective if and only if Dimension of kernel of T equal n minus m, which is the degrees of freedom. Difference between the unknowns and the number of equations, okay? And this is gonna be infinite number of solutions with the dimension. I will go to exercise with the next session. As I told you, today we will have 3 sessions. The first one started from 9:30 till the time being. I was really very happy to go through it. The second session, I will go some exercises on this part, which is really very interesting. And it has very nice examples. And the third session, I will make an overview about our course, and I will make a quick revision on one of the mock exams of midterm. Thank you very much. I appreciate it. I appreciate your existence today. If you're not here physically, it's not your spirit. Thank you.